Section 22 of Fires and Firefighters by John Kenlon. This LibriVox recording is in the public domain. Chapter 21. The Problem of the Skyscraper. Increasing land values due to congestion in large cities, coupled with advances in the mechanical arts and steel skeleton construction, have ushered in a new and perplexing problem for the firefighter. In American cities, there is no restriction placed upon the height to which an office or commercial building may rise, as long as certain regulations are complied with in regard to the material used. Height is not prescribed by law, but by economic conditions. Were it possible to provide inexpensive elevator service, there is no reason to doubt that buildings in New York would now have 100 stories, as there are already several with 40, and one with 57 floors. In the old type of factory or commercial building, ranging from 1 to 6 stories, the ordinary way of stretching hose lines by stairs and fire escapes provided all the necessary means for the firemen to reach the seat of an outbreak. But in these higher buildings, other methods had to be evolved. Standpipes running from the lowest to the highest floors were introduced. At first these were crude affairs, often misplaced and also deficient in size. However, experience soon discovered these defects, with the result that in New York an ordinance was passed, which it may be well to quote. In every building now erected, which exceeds 100 feet in height, unless already provided with a 3-inch or larger vertical pipe, and in every building hereafter to be erected exceeding 85 feet in height, and when any such building does not exceed 150 feet in height, it shall be provided with a 4-inch standpipe running from cellar to roof, with one 2-way 3-inch Siamese connection to be placed on street above the curb level, and with one 2.5-inch outlet with hose attached thereto on each floor, placed as near the stairs as practical, and all buildings now erected, unless already provided with a 3-inch or larger vertical pipe, or hereafter to be erected exceeding 150 feet in height, shall be provided with an auxiliary fire apparatus and appliances consisting of water tank on roof or in cellar, and such other appliances as may be required by the fire department. Standpipes shall not be less than 6 inches in diameter for all buildings exceeding 150 feet in height. All standpipes shall extend to the street, and there be provided at or near the sidewalk level with the Siamese connections. Said standpipes shall also extend to the roof. If any of the said buildings extend from street to street or form an L shape, they shall be provided with standpipes for each street frontage. As will be seen, this sets a minimum requirement of 4-inch standpipes for all buildings over 185 and up to 150 feet in height, and 6-inch for all buildings over 150 feet. In practice, it was found that a greater diameter was necessary in order to give more water for firefighting, and recently the diameter was increased to 8 inches in buildings over 150 and 6 inches for buildings under that height. At this point, a brief description of a standpipe, its equipment and operation, may not be out of place. The material used is generally galvanized, sometimes ordinary, black pipe. In the case of very high buildings, the main line must be connected by a Y at the street level, giving 4 3-inch inlets. These inlets to the Siamese have clapper valves, serving as checks to prevent the water from backing out. There is also placed a swing check to prevent the water in the pipe from backing out to the street connection when the line is not in use. This is to prevent freezing in winter time. The object of the pipeline, being connected to a tank on the roof, is to ensure a supply of not less than 3,500 gallons of water, which will enable the occupants of the building to hold in check an incipient blaze prior to the arrival of the department. All house supply lines for domestic purposes attached to the tank must be tapped in at such a height as to ensure at all times the quantity of water mentioned. A check valve is placed at the bottom of this tank on the standpipe line, set to permit a downward flow and to prevent an upward flow in case a fire engine or high-pressure lines are connected at the street level. The omission of this check would prevent pressure on the floor below, as water pumped in would merely overflow from the tank onto the roof. An open hose outlet on the roof will have the same effect, as the writer has more than once observed. Officers should carefully note these points in making inspections. Templates should be provided, and connections at street level and also those on the outlets on floors should be tested to see that they comply with department standards. It is a very serious matter when a dangerous fire is raging in the upper stories of such structures to find that the connections will not fit the hose and that water cannot be forced through the standpipes except through the medium of inside connections, a somewhat ineffectual expedient, but that hose lines must be stretched 12, 14, 16 or more stories. To the unthinking this may represent little, but to the experienced firefighter it means much. Very few men would be able to walk up 14 flights of stairs and then be fit for work on their arrival. Firemen in New York must often climb more than 150 feet, but it is impossible to drag hose lines up to such height. Also, the hose cannot stand the excessive pressure necessary to force water up to this elevation, and even if it were possible, the time employed in doing so would permit the fire to extend to such proportions as to destroy the building. With sufficient material on which to feed, a fire will extend in geometrical ratio to elapsed time, which again proves the necessity of speed in order properly to control an outbreak. All signs regarding pipes should be properly placed. Where there are 2 lines of pipe, one for the sprinklers or perforated pipe system and the other for the standpipe, a mistake or misplacement of the signs indicating their nature will cause serious delay and often great damage. At this point it may be well to state that perforated pipes are a poor substitute for sprinklers and should be taken out of all buildings and the latter installed in their place. The street connections should not be less than 2 nor more than 3 feet from the sidewalk level and at right angles to the building, which facilitates the work of connecting up. Should these connections be out of order, lines can be connected to the outlets on the lower floors by means of a double female connection. The method of procedure is to disconnect the house line, put on an increaser 2.5 to 3 inches, leaving a 3-inch male thread, and this connect to the double female. This will give a 3-inch female connection for the male end of the hose stretched from the engine or high-pressure hydrant. As soon as connection is made, open the valve and start the water. All outlet valves on floor outlets should be of the gate type, which gives a free waterway, whereas the globe type materially reduces the flow. Where several lines are being used on the upper floors of a building, and the 2 or 4 lines connected to the Siamese are overtaxed, the supply may be augmented by connecting to the lower floor outlets as previously described. In New York, standpipes are used in buildings so equipped when the fire is on or above the 5th floor. Below this point, the ordinary method is preferable. The hose provided in these buildings should be of good quality, capable of sustaining the pressure of 200 pounds, and be fitted with 1 or 1 1/8 inch nozzles. In many cases, through lack of attention on the part of owners or agents to keep the hose in proper condition, the firemen fear to trust it, and connect up a department hose using their own controlling nozzles for inside work. In order to describe the actual use of these standpipes and the pressure required to force water to the upper floors of buildings on fire, let it be assumed that there is an outbreak on the 16th floor of a 20-story building. The companies arrive and connect to the standpipe, and as the fire is a threatening one, 4 lines are led to the Siamese. Hook and ladder and engine company men proceed to the floor directly beneath the fire, by order of the chief, using the elevator for this purpose. The ordinance requires that night and day elevator service must be provided in all buildings over 150 feet in height. Each company has its instructions, and a battalion chief, in command on the inside, accompanies them. As soon as connections have been made to the Siamese, the chief officer must determine the pressure necessary to furnish effective fire streams on the 16th floor, or an approximate height of 170 feet. The formula for this procedure is to multiply the height of the building by .434, but here there is no time for pad and pencil. The best method is to allow 5 pounds for each floor of elevation, and at the height above mentioned it can be readily grasped that the result is 80 pounds, 7 pounds more than the exact formula, but which will be needed as the standpipe goes from the sidewalk to the basement and perhaps to the sub-basement. This gives the column additional length, and as the standpipe often makes a right-angled turn at the basement level, there is an additional loss of pressure at that point. Also, there is a nominal friction loss in the pipe itself. The writer's purpose is not to weary the reader with technical details, but it is necessary to explain this procedure for the benefit of commanding officers at fires at greater length than many other subjects with which firemen are more familiar. Therefore, 5 pounds will be allowed to each story for weight, about 4 pounds friction loss for each 50-foot length of 3-inch hose, 5 pounds loss at Siamese connections, and 10 pounds for entry head at the valve outlet on the upper floors. It will be assumed that there are 2 lengths of 3-inch hose in each line, giving 8 pounds, 5 pounds for Siamese, 80 for weight of water column, and 10 for entry head, making 103 pounds in all. Add to this the force necessary to give effective nozzle pressure, which would be from 50 pounds and upward, according to the extent of the fire, and the result is 153 pounds. This, of course, might be varied if a number of streams were taken off the standpipes, as the friction loss in hose and pipe is as the square of the velocity. That is, if water is traveling at the rate of 10 feet a second, the square of 10 is 100, but let the flow be increased to 20 feet per second, and the square is 400, or 4 times as much. Therefore, while the velocity would only double, the friction loss would be 4 times greater. Officers arriving at an outbreak find, as by a predetermined order, that the pressure on the mains is 100 or 125 pounds. They must judge instantly if additional pressure is required, and order it promptly, though it must be remembered that much damage may be done by excess in this direction. The writer once arrived to take command at a fire in a 5-story commercial building. The structure had 50 feet frontage and was 200 feet deep, and the fire had control of the 3 upper floors and was threatening surrounding property. The officer found in charge was asked what he had done and if additional companies had been summoned, as there was but a first alarm assignment at work. The reply was, "No, sir, I did not send out a second alarm, but I ordered 250 pounds pressure on the high-pressure pumps." This was soon after the installation of the high-pressure service, and officers had not yet mastered its proper use. In this case, 125 pounds was quite sufficient, or at most 150, to which point the pressure was immediately reduced and additional forces summoned. The very high and unnecessary pressure might have caused damage to hose, apparatus, pumps, or even men. Officers who wish to master these technical details should study them at leisure in their offices, so that they may be available for instant practice at a fire. The best method of fighting fires in lofts or office buildings of great height is to connect the first line at the outlet floor below the fire, lay the line out free of kinks, and stretch up the stairs. Charge the lines. Never be caught with an empty line in hand when the door is opened. Here is where many a man is injured, for his old enemy, backdraft, is just inside, and the moment the door is opened, it rushes out with superhuman force. Lie low, and like a pugilist duck the blow, and open up the pipe at once. Without going into a scientific discussion of the causes of backdraft, it may be well roughly to define it and to describe its action from a fireman's viewpoint. Plainly stated, it is an excessive pressure on a floor where windows and doors are all tightly closed. As the heat increases, the air expands, causing a greater pressure on the floor than the surrounding outside atmosphere. When a vent is given, there is a blowout, resembling an explosion, for the pressure must be equalized. In other words, the pressure on the floor must be brought down to the corresponding atmosphere on the exterior. The first explosion may be slight, but is often followed by a more dangerous outburst, depending upon the degree of heat on that floor. The influx of fresh oxygen supplies abundant fuel for the flames, and the smoke, which is part of the goods imperfectly consumed, bursts into flame and shoots through the opening. This condition must be guarded against, as men may be caught on the stairs and literally roasted. The sudden outburst of flame may also blow out windows on all sides, endangering surrounding property or the floors above. Another and still more dangerous form of backdraft is where a slow-burning fire consumes the oxygen in a building tightly sealed. A gas much lighter than air results, and this is particularly aggravated by the nature of certain kinds of goods. As is well known, different chemical changes take place in different kinds of material. A vacuum is formed inside the building, and as soon as the latter is opened, there is an inrush of air, which, coming in sudden contact with the gas, causes an explosion. The writer has often seen this peculiar phenomenon. The explosion is preceded by an awe-inspiring silence. Nature seems suspended for the moment while the two elements meet. In an instant, all is wreck and ruin. Men of experience instinctively feel this condition, and the order to back down and out is instantly given. Though, if in a position where they cannot get away at once, men should drop on hands and knees, covering their faces from the wave of flame, it may pass over without doing damage, when they should instantly arise and keep the pipe open while backing out of danger. Perhaps in all the science of firefighting, no part requires more care and attention than the opening of buildings on fire. Many brave men have lost their lives at this dangerous work. At a fire in the stockyards in Chicago, Chief Horan and 23 officers and men were killed just as the door was opened. There were no windows in the building through which the pressure could be relieved, and the wall gave way under the strain, burying all who were in front of it. Wherever such conditions are suspected, an opening should be made in the roof. This will relieve the pressure and is a fairly safe method. A brief reference must be made to the following important point. In cases where fire has complete possession of 1, 2, or 3 floors in a high building, beyond the reach of towers or turrets, great care should be exercised in placing lines above the outbreak. Companies of men with good streams should be at the doors below in order that the fire may not come out and cut off the retreat of the men above. Buildings of this class have more than one stairway and more than one standpipe, and the least exposed position should be chosen in advancing lines to the upper floors. No line should be sent to an upper floor until the companies operating the one below have gained a foothold inside the door, with a reasonable assurance that they can hold that position. Give as much ventilation as possible in order that the ascending smoke and heat may be minimized. Chiefs should avail themselves of rear fire escapes and every other possible point to get ahead of the fire, for should it once become uncontrollable on the upper floors, men cannot be kept in the building, and a collapse may momentarily occur. In all buildings of this class, fire towers should be provided. These are separate and distinct from the main building, and in order to reach them it is necessary to pass from the floor through a fireproof door onto a balcony outside the building, and through another fireproof door into the tower itself. Or, as a variant to this system, there is a plan whereby every building is to be divided into two sections by means of a firewall running from cellar to roof. This firewall would have fireproof doors on each floor, and there is almost no chance of a fire starting simultaneously in both parts of a building so divided. In case of an outbreak in one section, the people on each floor would walk through the fire doors to the other section, shut them on the fire, and take their time to reach the street, and firemen could easily gain a foothold on a floor subdivided in this manner. A standpipe in the former case should run from lowest floor to roof through the tower. Firemen could pass ahead of a fire and attack it on each floor with perfect safety. For rescue of occupants, this means, combined with the aforesaid horizontal fireproof partitions subdividing the floor area, would make these buildings safe for public and firemen alike. Add to these two indispensable requisites a thorough installation of automatic sprinklers, and the high building would be shorn of its terrors. In conclusion, the writer feels that after the foregoing pages, with their somewhat technical details from the layman's point of view, it may not be without interest to give some slight description of the greatest skyscraper in the world, the Woolworth Building of New York. Incidentally, this gigantic block of masonry was designed by its namesake as a memorial of his earthly success and to the glory of the commercial enterprise of America. Including basement and sub-basement, it consists of 57 stories and rises to a height of 790 feet above sea level, with a main frontage of 150 feet. Thus it will be seen that its height is 5 times its own width, and it is less than 500 feet short of the Eiffel Tower. It is, of course, of fireproof steel frame construction. The preparations for the foundations were begun in August 1911. On May 1, 1913, the doors were thrown open to tenants. This represents a period roughly of 20 months, during which time nearly 3 stories must have been added every 30 working days. Besides containing business premises, which incidentally are arranged as regards floor space to suit the wishes of the tenants, it is equipped with 2 restaurants, one in the cellar and one on the 29th floor, Russian and Turkish baths, a swimming pool, and an ice plant. All window frames within 30 feet of any other building are of hollow copper glazed with wire glass. It has 4 enclosed stairways of iron and marble, though only one extends to the top of the tower. There are 28 passenger elevators built on the most up-to-date fire-resistive principles. For the protection of the building, the following equipment has been installed. There are 6 6-inch risers running from the sub-cellar to the 30th floor, 2 from the 31st to the 41st floor, and 1 from the 41st to the 55th floor, fed by tanks on the following floors. 1 tank, 6,300 gallons, on 14th floor, feeds from sub-cellar to 12th floor. 2 tanks, 10,000 gallons, on 26th floor, feeds from 13th to 24th floor. 1 tank, 3,100 gallons, on 37th floor, feeds from 25th to 34th floor. 2 tanks, 1 6,700 gallons, 1 3,200 gallons, on 50th floor, feeds from 35th to 48th floor. 1 tank, 1,200 gallons, on 53rd floor, feeds from 49th to 53rd floor. There are 4 outlets above this tank with no supply. The main riser, 6-inch, has checks on the 14th, 27th, 37th, 50th, and 53rd floors, with checks on the horizontal run. There are 2 suction tanks in the sub-cellar, one 30 feet by 9 feet by 9 feet, one 15 feet by 9 feet by 9 feet. There is a swimming pool in the sub-cellar Turkish baths, which can be used as a suction tank, with a capacity of 30,000 gallons. There is one Dean electric pump, 3.5 feet by 6 feet, with a capacity of 300 gallons per minute. There are, in addition, 5 Worthington steam pumps as follows. One 20 feet by 9 feet by 18 feet, 500 gallons per minute. One 20 feet by 10.5 by 15 feet, 500 gallons per minute. One 14 feet by 6.5 by 15 feet, 150 gallons per minute. One 14 feet by 6.5 by 10 feet, 150 gallons per minute. One 12 feet by 4.5 by 10 feet, 80 gallons per minute. All pumps can be operated singly or collectively, and are supplied by street mains as follows: one 6-inch from Broadway, two 3-inch from Park Place, two 3-inch from Barclay Street. Such are a few details of this extraordinary structure, which may be expected to house daily some 10,000 souls, and there is no reason to believe that finality has been reached. Room must be found for the teeming thousands who throng to the business section of New York, and expansion must occur by the way of least resistance, upward. End of section 22. Recording by Maria Casper.